we just had a chance to look at some emission spectrums, and we're going to talk about where they come from and then how you can use these spectrums to understand the Bohr model a little bit better. Okay, so let's call this the Bohr model of the atom. All right, so the experiment that we did was to take a high voltage source here. So I'm just going to draw a little quick circuit diagram. Right, so this represents a high voltage, and we took a tube, so a glass tube, and that tube was filled with hydrogen gas. And we found that when we ran a high voltage, and we're talking like 5 kilovolts, so like 5,000 volts, that we saw like a bluey kind of purpley light shine out of there. Okay, and then what we did was we took our spectroscopes. We looked at that. Okay, so there's your eye peering in. And what a spectroscope does is, much like a prism, it takes whatever light is shone into it, okay, and it more or less, I mean, it uses a grating, but you don't need to worry about that. It more or less bends the light, but it bends different wavelengths of light slightly differently. So that white light actually separates out into its component colors, all right? So if you take your spectroscope and you look at sunlight, you would see an entire rainbow. You know, so you get your like Roy G. Biv kind of thing. And I'll just draw this here quickly. So that's your, you know, your prism is doing this. And this light is then visible on whatever surface. You might get this effect too if you hang like a crystal in your window or something like that. So it's taking the components of the light, which your eye adds together for you and you see as white, and separating it out into your rainbow. So that's an entire full spectrum. So if we take our spectroscope here and we look at sunlight, much like a prism, we see all the colors of light. But if we look at the hydrogen tube, we see something different. I'm going to show what we see. Okay, so just to pick up where what we were talking about here, the hydrogen emission spectrum. So what you see when you look at the hydrogen tube looks like this. Okay, you might not have been able to catch all these lines, especially this purple one way over here. Sometimes hard to catch. Actually, both these purple ones are hard to catch, but they are there. But if you look at sunlight, you see the continuous spectrum. So white light separates out into your complete rainbow of light. All right. So back around the turn of the century, physicists were trying to figure out like what is going on here. Why is it that when we look at an emission from something like a hydrogen tube, we're seeing this, versus when we look at sunlight, we see all of this? And they extended that to other gases, and they found that each one had a different pattern of light. So if you look here, and actually these are inverted, but you see red, right? You see a bit from the blue here, and you see some purple from there. So what we're actually seeing is just parts of this overall continuous spectrum. Don't worry about emission and absorption just yet. But when we look at hydrogen, this is what comes out of it. So this is where we bring in the Bohr model. So you've probably learned what a Bohr model looks like, but not maybe necessarily why it is the way that it is. So Niels Bohr was a physicist, and right around this time, a whole bunch of information about the quantum nature of the universe was sort of coming out, and how Bohr explained why you get this was like this. So he said, hydrogen has a nucleus, and inside the nucleus there's one proton, okay, and for most hydrogen there's no neutrons, but there are some isotopes with neutrons. We're not necessarily interested in what's going on inside here though. For this, what we're looking at is the fact that there's one electron outside here. And you know from the Bohr model that it has these rings around it, right? And we know that the rings fill 2, and then the next ring can hold 8, and then the next ring can hold 8, and then you get like the next ring and it holds 2, and then all of a sudden there's like transition metals all in here. We're just going to concentrate on the simplest, right, atom, and that's hydrogen. Okay, so Bohr said that there's a ground level where this electron is in its lowest energy state, right? It's just kind of hanging out here. Remember we said though, in our little video, or in our little discharge tube, we're putting 5,000 volts across tubes filled with hydrogen gas, right? So electricity is like flowing through this gas, and it is exciting it. Okay, so it's putting energy into these electrons, and it turns out that these other rings or shells or energy levels or orbitals or whatever you want to call them are actually sitting there, but they don't have anything in them. So what ends up happening is electricity comes in here, it gets absorbed into this electron, and if the right amount of it gets absorbed, then this electron will pop up to higher energy levels, and it might go all the way up to very, very high energy levels. And if enough energy is put in, it'll actually like peel that electron off, and it'll do what's called ionizing, ionizing the atom. All right, but we're not going to go there. We're just going to say that the electron can get popped up to some higher energy level. We don't know which one it goes to, but some higher energy level. Okay, and if you imagine a tube, this is happening to billions and billions and billions of atoms at one time. Okay, so they're getting excited, their electrons are popping up. Well, it turns out that excited electrons will fall back down randomly at random times to lower energy levels. Now, this is the first or the ground state level. This is the second level, the third, the fourth, the fifth, and the sixth. I think that's all we need. And the ones that actually like show visible light are when electrons fall back down to the second level. Okay? So they might fall from the third to the second, from the fourth to the second, or from the fifth to the second. And it turns out that the colors of light are associated with the amount of energy carried by what's called a photon of that light. Now, it's a little more complicated than we need to actually get to, but essentially, an excited electron, an electron that's been promoted somewhere above the ground state, needs to get rid of its extra energy to fall back down to a lower state. The farther it falls, the more energetic that energy is that it kicks out. The type of energy it kicks out happens to be, if it falls to the second level, in the visible range. So it kicks out electromagnetic energy. So if it falls to here, it gives off a flash of red light, or a photon of red light if you want to get a little more complicated. Okay? So that explains this guy right here. If it falls a little more energetically, we're going to get that blue color. So if it falls from the fourth down to the second, we'll get that blue color. And if it falls from the fifth down to the second, we get the most energetic light, and that's the purple color. Okay? So these lights that we see, these parts of the spectrum that we see here, correspond to the electron falling from higher levels down to the second. So then you might ask yourself, well, what happens if the electrons fall back to the first level? And that does happen, except the thing is, that light is so energetic when that happens that it's in the ultraviolet range. So you've probably heard of ultraviolet light, high energy light that comes from the sun that you have to wear sunscreen to protect yourself from. Well, this thing is actually giving off ultraviolet light as well, which is why we don't spend a whole lot of time running it. Ultraviolet light's not good for you. But there is another area in the spectrum that is in the ultraviolet that you just can't see. Okay, so just to continue, what this represents here, okay, are the energy levels that we were talking about, okay? So the energy levels above that bottom ground state. And it's actually been measured into how much energy there is associated, or potential there is between these levels, measured in electron volts. You don't really need to worry about that. But here they are falling to the second level, okay, and that's called the Balmer series. That's what we can actually see. Then here they are falling into the UV, giving off so much energy, more energy than the amounts of, or than the visible spectrum. So that's in the UV spectrum. And then there's actually some, if they fall to the third level, right, that are low enough energy that they're in the other side of the spectrum, which is the infrared, okay? So we can talk about the full electromagnetic spectrum for just a second, and hopefully make sense of that. So here's a full spectrum, and just something interesting to note here is that you are only able to detect light that's in this region of the whole big thing, okay? So, you know, you've got AM radio down here with longer waves, right? Soccer field length waves. FM is a bit shorter, so a bit higher frequency. Your microwave oven's way down here. It is non-ionizing radiation, so your microwave is not going to cause, you know, cell mutations and so on. There's radar. Here's infrared. Your oven often will cook your food with infrared as well as with convection. So infrared's there. Then visible light. Then we get into what's called ionizing radiation that you want to avoid contact with. So anything to this side, I can't draw this well. Anything to this side is where you get things like cell mutations caused by coming in contact with this type of radiation. So X-rays and gamma rays and so on, you want to try to avoid as much as possible. And even ultraviolet, like UV from the sun, is not good for you. And that's why we have sunblock, okay? So any nonsense about microwave ovens being able to cause mutations, just shake your head at the person, okay? Because that can't happen. Now, just back to here. Here's UV light. Okay, it's beyond what we can see, but the hydrogen does put it off. Here's what we can see, the Bomber series, it's right in there. And then there's the Passion series, which is in infrared, which is longer wavelengths or lower energy, okay? So the Bohr model is just an explanation of why we get these, and it's a quantum model. It's saying there's a specific quantity of energy associated with falling each of these levels. And the other thing about it is that the electrons can never, ever exist in between them, which is sort of weird, right? Like if you think about nature, I mean, most things work on a spectrum. You can move something however far you want from left to right. So why is it that an electron can only be in one place or another? It can never be in between. And it's one of those things where that's just the way nature appears to have constructed itself. I know, I can't give you a better answer than that. That's kind of just the way it is. So when we say quantum physics, we're talking a lot about these quantities of energy that are associated with different atoms and what their electrons are doing. Okay, so if you up the ante and you go from hydrogen to helium, you get a completely different spectrum. Okay, so something else that's kind of interesting here when we're talking about spectrums and so on. If you look with a very, very good spectroscope at the light coming from the sun, you'll actually notice that there's these weird like black lines lining up on this spectrum. And scientists were like a little bit baffled as to what that could possibly be. Like, why do these weird lines pop in here? But if we roll back and we look at an emission spectrum, way back here, okay, way back here, what they noticed is that these black lines seem to actually line up with the emission spectrums from different gases you might find here on Earth, okay? Now, why is this happening? Well, it turns out that if I shine full spectrum white light through hydrogen or through helium gas, all of the wavelengths that exactly correspond to these guys jumping up will also be absorbed. So it's like a two-way street. When they're falling back down, they kick out a specific color of light. But if they're in a lower state or in this state, as light shines through, they'll like absorb the light and that will pop them back up to another level. So from deep inside the sun, you're getting a full spectrum of light emitted, but the outer layers of the sun have some gases in them, hydrogen and helium specifically, that are also absorbing in those very specific ranges those colors of light. And the electrons in those gases are popping up and down and not allowing that light to shine through, okay? So we call that an absorption spectrum. And that's what these lines on the solar spectrum are from. They're from helium, mainly helium, sucking in light of those wavelengths. And it turns out helium is a pretty rare gas. It's really light, and it tends to like float upwards. If you've ever had a helium balloon, you know that. And it's so light that helium floats off the Earth into space, okay? So, yeah, and helium's also a noble gas, right? So it doesn't react with anything. So it was really hard to discover helium, and in fact, its discovery was from looking at solar spectrums and saying, wait a minute, we have all these gases that we know the spectra from, but there's none that exactly match this absorption spectra. There must be a gas in the sun that we don't know about yet. And in fact, that is how helium was originally discovered. In fact, the name helium is named after the name of our sun, which one of its names anyway is Helios, which I think is the ancient Greek name for it, or the sun god was Helios. I think that's where that came from. And that's where helium comes from, because it was discovered in the sun from absorption spectra. Later, scientists went and looked for it, and now they found that I think where it usually comes from is if you have a natural gas deposit under the earth, usually they're trapped under like salt domes, because natural gas would tend to float away too. But amongst that natural gas under the salt dome, often they find helium. And it's a byproduct of the radioactive decay of other heavier elements, if you want to know where it comes from. So there you go. And helium is a limited resource on Earth, actually. You could almost say the Earth is running out of helium. And that might be something to be concerned about, because it's sort of required for, say, supercooling electromagnets and so on, so that you get superconductivity. So helium is required for that. So you want to kind of conserve helium. Might be interesting. I've heard it said that in 100 years people will look back and just shake their heads on the fact that we wasted helium on party balloons. But who knows? So what I put here, just as a final note, here's that kind of solar spectrum, right? The full color spectrum with no lines in it is a full spectrum, but the solar spectrum does have these lines. You can see sun here. There's hydrogen, and you'll notice some of these black lines, right, are lining up with where they would be in the emission spectrum, right? So it's the opposite effect, right? So what's happening here is these black lines are appearing because these electrons that were normally falling down are now getting promoted, and they're absorbing that energy, and hence the black line. There's helium. You can see that line lines up with the helium emission spectrum. It's not quite exactly perfect, but it's pretty close. Okay, so these lines line up, and you can find different elements in stars by looking at what lines they have for absorption. So you can actually look at a star that's many light years away, look at its spectrum, and you can figure out the composition of gases that exist inside that star simply by looking at the spectrum. So that's kind of neat, and it all really comes down from the Bohr model. Okay, now the Bohr model doesn't do a great job because it gets too complicated essentially. So when we get to helium, okay, it's not quite as simple to explain, right? Well, it's just electrons falling down, and quantum physics is much more complicated than just simply rings with electrons falling up and down. But you can imagine when we go from 1 now to 2 electrons, and they're zipping up and down, and they're going up and down to different levels and so on, that the pattern you'd get out of it is more complex. And as the atom gets more complex, so does the spectrum it gives off, right? So there's uranium down at the bottom with like 92 electrons all zipping up and down, and you get this kind of bigger picture here. So we'll wrap it there.